Hi everyone, my name is Zeinab Bandpey and I'm a PhD student at Morgan State University. Today I'm going to talk about Jonathan Farley's mathematical terror theory, the structure of perfect terrorist cells with a single leader. In this paper, terrorist cells are modeled as finite, partially ordered set. This paper determines the structure of terrorist cell is mostly to remain intact if a subset of its members are captured in random. And we're considering a cell with one single leader and no element has more than B immediate subordinate. We proved that the cell with the fewest cutset, which is the number of people you can capture to destroy the whole cell, is a specific kind of poset that we call fishbone poset, and I'm going to define in a minute. To give you a background about the people who have worked on this problem before, Dr. Farley proved the conjecture for B equals 2, meaning we have like a poset in which any member has at most 2 lower covers or 2 immediate subordinate. Vašek Chvátal and 3 other computer scientists at McGill University proved the special case for trees. And also, U.S. Army gave Dr. Farley about $20,000 to write a monograph entitled Toward the Mathematical Theory of Counterterrorism. What I proved in this paper, and I'm going to talk about today, is mathematically speaking, I'm going to talk about if you have in the class of partially ordered set with any element doesn't have more than B lower cover, what will be a structure of a poset with the fewest cut set? And again, this slide gives you a story about people who have worked on this problem before. So this conjecture is proposed by Dr. Farley. He was giving a talk at McGill University, and Chvátal and other computer scientists were there, and they heard about the question and conjecture, and they worked on the special case for the trees, and they published their work at Journal of Graph Theory. At the same day, Dr. Farley proposed this question that I solve now, and I would like to consider, they couldn't solve it, or so. All right. So a common way to represent visually a group of people who are interacting with each other is by concept of graph theory. Individuals are represented by nodes, and if 2 people are in relation in some fashion, a line is drawn between them. In the case of terrorist cell, one might draw a line if 2 individuals are interacting directly. The leader is represented by the topmost element. The foot soldiers are the bottommost nodes in the graph theory. And then they have name in mathematics too. The topmost element is maximal element, and the foot soldiers, which are the bottommost elements, are minimal elements. And the link of command from top element to the bottom element is a maximal chain. But I'm going to show them in this picture. So here, if I want to talk about the terrorist theory, the topmost node is this one, which is leader, and these are bottommost nodes, which are foot soldiers, and the link of command from here to the foot soldiers is a maximal chain. So, but to write it down more clearly, let's say we have this poset. And I'm going to call them A, B, C, D, E, F. So the maximal element is this one here. And these 2 guys are minimal elements. And if I want to show a maximal chain, it's A, B, C. So it starts from the top element and it goes to one of the minimal elements. So this is a maximal chain. All right. So again, the theorem that I proved in this paper is the poset with the fewest cutset in the class of finite B-array poset with one top element is fishbone poset that I'm going to introduce in a moment. So I kept talking about poset. What is poset? Poset is a partially ordered set with a binary relation, but this relation should be reflexive, antisymmetric, and transitive. Reflexive meaning it means any member is in relation with itself. Antisymmetric if there is a member who is in relation with the other one and the other one is in relation with the first one, then these two members should be equal. And the last one, if you have member X which is in relation with member Y and you have member Y which is in relation with member Z, then X is in relation with Z as well. So that's a partially ordered set which we call poset. Now, I talked about like immediate subordinate. In mathematics, we call it like lower covers. And we say X covers Y if there is, like X is above Y and there is no other elements between them. So if you look at this example that I have here, I can say A covers B because A is above B and there is no other element between them. And also A covers C, A covers D, or C covers E, D covers F, and it goes on like that. A chain, we talked about maximal chain, but to give you a definition for chain, like generally, is a totally ordered subset of a poset. It means it is a subset of poset. Any two elements that you take from this subset, you can compare them by each other, like what I wrote here. ABE is a chain. ADE or AD by itself they are chain. But if I say ABC, then this is not a chain because you cannot compare B and C by each other. There is no line between them. They are not in relation, and so ABC is not a chain. And then we have anti-chain. Anti-chain is a subset of poset in which any two elements are incomparable. If I want to give you an example for anti-chain, I would say B, C, D, because like B and C, there is no line between them. They're not in relation. You cannot compare them. C and D, you cannot compare them. And B and D also are incomparable. Or another example will be E, F. So this is an example for an anti-chain too. But if I say E, F, C, this is not an anti-chain because this F and C and E, you can compare them together. So anti-chain is a subset of poset. Any two elements that you take cannot be compared together. All right, so we know what is chain, what is anti-chain. We know that the concept covers. I talked about maximal chain, so it is a chain which is not subset of any other chain. Now, I said A covers B, so B is lower cover of A. Now, for any node that we have in the poset, we can define LC of P for any P in the poset P. It is the set of lower covers of P. For instance, if the poset is this one, I'm going to add this too. And I'm writing down lower covers of A. I should write any elements which is covered by A. So this is B, C, and D. And then one of the most important definitions in this paper is K cutset. K cutset is a subset of poset which has like K members, and this subset intersects any maximal chain in the poset. For instance, if I want to show, let me use the same poset here, and I'm looking for, let's say, 3-element cutset. So it should be a subset of this poset, which has 3 elements. And these sets should intersect any maximal chain in the poset. So if you look at maximal chains here, this is a maximal chain, a chain which starts with the top element and it goes to one of the minimal elements. So this is a maximal chain, this one is maximal chain, this one is maximal chain. And I want to pick 3 of this 1, 2, 3, 4, 5, 6 members which intersect any maximal chain. So if I pick the top element, this top element is point of intersection with all the maximal chain here. So if I pick A, then I can randomly pick any other 2 members to create 3 cutsets. But if I don't want to have top element, then the 3 cutset will be a set of 3 elements which intersect any maximal chain here. So it should contain these 3 elements B, C, and D. So definition of cutset, K cutset is a K member set which intersect any maximal chain in the poset. Then we have this terminology. If I use cut PK with capital C at the beginning, it shows the set of K cut set of P. If I use it with the small c at the beginning, it shows the cardinality of the first set. All right, one quite useful observation here. If we have a poset with greatest element T, and this top element has n lower cover, x1, x2 to xn, and then if we ignore one of these elements and instead take lower covers of that element, then that will create a lower cover as well, a cut set as well. So just let me explain it in an example. So let's say I have this tree, or I can make it a general poset and go for tree. So this is the top element. I'm going to show it by T. Then I have x1, x2, x3, x4 as lower covers of T. And then I'm going to call this one and this one A and B respectively. So what this observation says, it says, so the T is top element. It has a x1, x2, x3, x4 as lower covers. And if you ignore one of these, so we know that this x1, x2, x3, x4 is a 4 cut set of this poset because it has 4 members, and it intersects any maximal chain in the poset. So what this observation said, it says if I ignore this x1, let's say I'm taking this one out, instead I'm using the lower covers of x1. So I have A, B, x2, x3, and x4. Then this new set is a cut set of the poset by itself. Because if you look at all the maximal chains here, you can find at least one member in this set which intersect that maximal chain by itself. So I took out sorry, x1. You can go for x3 and instead substitute these 2 numbers, and or for x4 as well. All right. I also, when I talked about the theorem that I proved in this paper, I said in the class of partially ordered set in which no element has more than B lower cover. So if we have a poset for which no element has more than B lower cover, we call it B-array poset. And to write it down, so LCP is the number of lower covers of any element B here. So to have the poset be B-array, thus LCB should be less than or equal to B for any element of the poset that we have. And here is the definition of fishbone poset, which is a special kind of poset, and later on I'm going to prove this is the poset with the fewest cut set in the family of B-array poset. So how did we define it? Fishbone poset of 0 element is empty set. It doesn't have any element. If it is, it has one element, then it's just one node, just like this. So this is fishbone poset of one element. If you have 2 elements, it goes like this. But for any n between 0 and b, then you have this top element and b minus 1 lower cover. But if n is greater than b, so that's how you write it down, like we wrote it down. It's this n minus 1 with this underline. It means anti-chain with n minus 1 element. And this plus sign that you see here, it's like an addition in order set. It says like if you have n minus 1 element here, let's say x1, xn minus 1, and then this is top element. When you have this plus sign, it means you draw a line between these n minus 1 element and the top element. So it gives you the same poset that you had before. That's just the way that you can write it down. And then if you have more than b elements, then you have this top element. The top element has b lower cover, and then one of this has lower covers, and it goes on. So that's a structure of fishbone poset that you can see in the next example more clearly. So the first one is fishbone poset. Like we are talking about 4-array poset, meaning no element has more than 4 lower cover here. So first one is just one node, that's 1 element poset. Second one, 2 element, and for any n less than 4, like less than 4 plus 1 or 5, you see that you have top element and the lower cover. But when it is more than 5, then one of these nodes is going to have like more lower covers, and it goes down to this. But as you can see, the other lower covers of the top element don't have any branches or any lower covers here. So that's the definition of fishbone poset. But before getting to the main theorems, I'm going to talk about 2 lemmas, which is proved by Dr. Farley in his paper. The first one is P is like n-member poset, and it has one single leader, R. Then the number of k-member cutset containing R is just choice of choosing like k minus 1 element out of n minus 1 element. I'm not going to go through the proof, but I'm going to explain quickly why is that the case. So when we talk about k element cutset, k member cutset. As we said before, this is a k-element set which intersect any maximal chain in the poset. But when it contains top element, so it has point of intersection with any maximal chain, because this is a top element, or they call it R in this lemma, so let me call it R. And then let's say this is the poset I have. All right. So if you look at any maximal chain that you have here, this R is point of intersection with any maximal chain. So let's say this poset P has n elements. It has less, n is like a particular number here, but in general case. Then you want to choose k member out of this n member, but since you have this element R, which is the top element, and it is the point of intersection with any maximal chain, it doesn't matter what are the other k minus 1 members. You can randomly pick any k minus 1 members out of this. That's why you say this is n minus 1, k minus 1. Or to be more clear, let's look at an example. Let's say this is my poset. It has 1, 2, 3, 4, 5, 6 elements. So cardinality of P is 6. And I'm looking for 3 element cutset. So as I said, and it includes the top element R. So one of these 3 elements is R, so I'm looking for 2 other members. This R is already taken, so I can pick 2 elements out of those 3, 5 elements. So it's simplified as choice of 2 out of 5, which is what this lemma says. All right. The other lemma is just for trees. It's not for the general case. It's not for any partial order set that you have. But we proved the same theorem for the general case for any other like partially ordered set, which is not tree. But what this lemma says is if you have a tree like this one, I'm gonna make it a little bigger. All right, so if you have a tree and this tree has B immediate subordinate, meaning it has B lower cover. In my case, it has 4 lower cover. And then it says when you ignore the top element, if I ignore this top element, then I should ignore all the lines which coming down from the top element. Then what do I have? I have this one, then I have this subposet, then I have this subposet, and I have the last one. All right, so you see when we ignore the top element, we would end up with 4, in my case, 4 subtrees, which are like the smaller trees. And I'm going to call them T1, T2, T3, and T4. And there is no line between them, right? So that's what the lemma, the first part of the lemma says. It says if you have the top element and top element has B lower cover, when you ignore the top element, then you would have B smaller trees, which is called T1 to T. B, in my case, T1, T2 to T3, T4. But this is not the main point of this lemma. It says when you're looking for cut sets, K cut set of, let me call it M cut set to be. When you're looking for M cut set of the original poset or original tree T, which doesn't contain the top element, you can look for M1 member here from the first tree, M2 member from the second tree, M3 member from the third tree, and M4 member cut set from the fourth tree, such that M1 plus M2 plus M3 plus M4 equals to this M here. So you can break it down and take some members from the first tree, some from the second, some from the third, and some from the fourth tree. That's how you can find a cut set for the original tree that you have before. For instance, if I want to find, let's say, 13 element cut set of this original tree, then I can look for 3 element cut set here. And then let's say 4, we don't have 4 member here, 2 element cut set here, and then 5 element cut set here, and 3 element cut set here. And then if you put all of them together, that will be a 13 element cut set of the original 3 plus 2, 5, 5, 5, 10, 10 plus 3, 13, which is the same number we were looking for the original poset. And now for next one is like the same concept, but what it says when you have this tree and the top element has B lower cover, but B minus one of them don't have any other lower cover. In the case will be like this. So this is a tree. It has B lower cover, let's say x1, x2, x3 to xb. This is top element. These B minus one element don't have any other lower cover, but this one goes down. Let's say that will be an example for this. So when you ignore the top element, you have the subtree or the smaller tree, better to say. And then you have x2, x3 to xb, which is anti-chain of B minus one element. So when you're looking for m-member cutset of this original poset, which doesn't contain the top element, you can look for m minus B minus one element cutset of this small tree, and then take the union with this B minus one element. So these two lemmas are kind of the same. This is like the special case of this one when these elements here don't have any lower cover. All right. So from now on, the theorems that you're going to see are the theorems that we proved by ourselves. The first theorem gives you a tool to compute the number of m-member cutset in a fishbone poset that you have. We proved this theorem using induction on S, but I'm going to show you how this theorem works just in an example. Then we can go through the proof by itself. So it is a fishbone poset. It says FB fishbone poset, P1 has K1 immediate subordinate, P2 K2, and it goes to PS, and KS is 0. So just to give you a structure of this poset, so this is P1, P1 has K1 lower cover, and then you have P2, P2 has K2 lower cover, and it goes on to PS. Let me go for PS minus 1. It has KS minus 1 lower cover, and PS, which is this one, doesn't have any lower cover. So this is the structure of fishbone poset, and we're looking for K m-member, or let me just look for its m-member cutset. So we want to find cut PM, meaning the set with m-members which intersect any maximal chain here. So I'm going to take care of different possibilities that we have. If this m-member set contains the top element, this top element is point of intersection with any maximal chain, then I can pick the m minus 1 other member randomly. So that will